Linear acceleration. Linear acceleration. Okay. For the study of nuclear reaction, charged particles having energies of many millions electron volts are required. For the study of nuclear reaction, charged particles having energies of many millions electron volts are required. It is difficult to generate a direct voltage of the order of 10 million volts, chiefly due to insulation difficulties. Okay, okay. Then to obtain a linear acceleration of a charged particle in excess of 10 million electron volts, indirect methods are used. The first type is known as drift tube acceleration and the second type as waveguide acceleration. Let us discuss first type of linear acceleration. Okay, linear acceleration. A linear accelerator or a linear is a device which accelerates charged particles in a straight line by means of oscillating electric field that provides either a series of steady accelerating steps in correct phase as a series of gaps between electrodes or accompanies the charged particles as a traveling wave. Okay, a linear accelerator. A linear accelerator. A linear accelerator or a linear is a device which accelerates charged particles in a straight line by means in a straight line by means of oscillating electric field. Okay, that provides either a series of steady that provides either a series of steady accelerating steps in correct phase at a series of gaps between electrodes are accompanies the charged particles as a traveling wave. Okay? In a linear accelerator, a moderate accelerating potential is applied a number of times so that the charged particles are accelerated along a straight line. A simple form of the linear accelerator you can show. Simple form of linear accelerator. Ions. To target. One, two, three, four, minus, plus, minus, plus, HF oscillator. HF means high frequencies oscillator. High frequency oscillator, okay? High frequency oscillator, okay? The charged particles are ions travel through an aperture A and move along the axis of a series of coaxial cylinder electrodes 1, 2, 3, 4, etc. These cylindrical electrodes are known as drift tubes. Drift tubes. Okay? The drift tubes are connected to an AC source. The drift tube is connected to an AC source of a very high frequency, say as a high frequency HF oscillator. Okay, so that alternate tubes have a potential or opposite sign. Thus, in one half cycle, if tubes 1 and 3 are positive, then 2 and 4, then 2 and 4 will be negative. After half cycle, the polarities are reversed. 1 and 3 will be negative. 1 and 3 will be negative. Negative, and 2 and 4 will be positive. Okay. Suppose opposition ions leaves A. Suppose positive ions leaves A and is accelerated during the half cycle when the drift tube number 1 is negative with respect to A. If capital V is the potential voltage of drift tube and 1 with respect to A, then velocity 1 by 2 mv1 square equal to ve. Okay, then v1 equal to under root of 2ve upon m. Okay, where E is the charge and m is the mass. Where E is the charge and m the mass of the ions. The mass of the ions. Mass of the ions. Okay? Mass of the ions. It is supposed that B1 is small as compared to C. It is supposed that B1 is small. B1 is small. It is supposed that B1 is small. B1 is small as compared to C. As compared to C, the velocity of the light. The velocity of the light. Velocity of the light. Okay. Velocity of the light. Where B1 velocity. B1 the velocity of ion. B1 is velocity of ion. Velocity of ion. Okay. Velocity of ion. Then if B1 is small as compared to C, the velocity of light, so that the change in mass due to relativity effect is negligible, the ions are accelerated in the gap between the tubes. Okay, but travel with constant velocity in the filled free space within the tubes themselves. The length of the tube one is so adjusted that as the positive ions come out of it, the tube has a positive potential, and the next tube number 2 has a negative potential. The potential charge sign, the positive ions, is again accelerated in the space between the tubes 1 and 2, and reaching the tube 2, its velocity v2 is given by 1 by 2 mv2 square equal to 2ve equal to 2ve. Then v2 equal to under root of 2ve by m equal to under root 2v1. Okay. This shows that V2 is root 2 times V1. V2 is root 2 times V1, okay? This shows that V2 is root 2 times V1. In order that these ions are coming out of tube 2, maybe find tube 3. Just negative. And the tube 2 positive, it must take the same time to travel through the tube 2, as the velocity is root 2 v1. The length of the tube 2 must be root 2 times the length of tube 1. Okay? The length of tube 2, then the length of tube 2, the length of the tube 2, must be root 2 times, root 2 times the length of tube 1. Okay? For successive acceleration in successive gap, the tube 1, 2, 3, 4 etc. must have length proportional to 1, root 2, root 3, root 4, etc. Okay? For successive, for successive, for successive, successive acceleration, successive acceleration in a gaps, in a gaps, the tube 1, 2, 3, 4, etc. must have, must have, must have length, must have length proportional, proportional to 1, root 2, root 3, root 4, etc. Okay? To a first approximation. To a first approximation. Approximation. To a first approximation. Okay? To a first approximation. Okay? To a first approximation. To a first approximation. Okay? Next. Energy of the ions. Energy of the ions. Okay? One minute. Energy of the ions. Of the ions. Okay? Energy of the ions. If n is the number of gaps that the ions travel in the accelerator and Vn is the final velocity acquired by it, then velocity of the ions as it emerges out of the nth tube, Vn equal to under root n under root 2 Ve upon m. Okay? Where n number of gaps. N is the number of gaps that ions travel in the accelerator, and Vn is the final velocity acquired by it, and Vn is the final velocity acquired by it. Okay? A kinetic energy of the ions. Kinetic energy of the ions. Kinetic energy of the ions. 1 by 2 mvn square equal to nve. Okay? The final energy of the ions when they strike target depends upon the overall length of the accelerator, the total number of gaps, and on the energy gained in each gap. The beam striking the target consists of pulses of particles. The number of pulses per second is equal to the frequency of the alternating voltage applied to the drift tubes. Okay? Length of the cylinder. Length of the cylinder. Length of the cylinder. Okay? Length of the cylinder. Or the ions is accelerated in the gap between two cylindrical electrodes. The times taken by ions to travel through the cylinder should be equal to half the time period of the high frequency voltage, so that each time the ions comes out of the cylinder, the polarity changes. If Vn is the velocity of the ions, the time of passes through the nth cylinder of length Ln, then T equal to Ln by Vn equal to T by 2 equal to 1 by 2 F. 1 by 2 F, where F is the frequency of the oscillator's electric field, where F is the frequency. F is the frequency of the oscillating electric field of the oscillating electric field. Okay. Then ln equal to Vn upon 2F equal to 2nVe upon m power 1 by 2 1 upon 2F. This equation shows that the length of the successive cylinders had to be increased in order to get a resonance acceleration of the ions at each gap, and length ln is directly proportional to the power n to the power 1 by 2. Limitation. Limitations. Okay. The limitations of the linear accelerators are: first, the length of the accelerators becomes inconveniently large, and it is difficult to maintain vacuum in such a large characters. Okay. The length of the accelerator becomes inconveniently large, and it is difficult to maintain. It is difficult to maintain a vacuum in such a large chamber. Vacuum in such a large chamber. Okay. Large chamber. Second, the ion current is available in the form of pulses of the short duration. The ion current is available in the form of pulses of the short duration. Pulses of the short duration. Okay. Circular accelerator. One minute. A circular accelerator is another example of the drift tube accelerator. Circular accelerator is a device which can accelerate charged particles by passing them again and again in a radio frequency RF. Okay, electric field along a closed path. Familiar examples are cyclotrons, which accelerates protons, neutrons, and alpha particles, and betatrons, which accelerates electrons. Okay. Circular accelerator is a device. Circular accelerator is a device. Circular accelerator is a device which can which can accelerate charged particles, which can accelerate charged particles, accelerate charged particles by passing them and again, by passing them and again, by passing them and again, and again, again, in a radio frequency, radio frequency RF, electric field along a closed path, electric field electric field along a closed path, okay, a closed path. Familiar examples: first, electrons, which cyclotrons, cyclotrons, which accelerates protons, accelerates protons, deuterons, and alpha particles, okay. Second, beta-trans, which accelerates electrons, okay. Next, waveguide accelerator, okay. Waveguide accelerator, okay. Waveguide accelerator, okay. Waveguide accelerator makes use of electromagnetic radiations wave traveling in a waveguide to accelerate charged particles. A waveguide is a hollow pipe. Cylindrical or rectangular conducting material in which oscillating electromagnetic fields of the order of 10 to the power 5 megahertz, 10 to the power 5 megahertz can be established if the electromagnetic wave is fed at one end of the waveguide and there is an electrical conductor at the other ends. The advancing and the reflected waves superimposed to form standing or stationary wave. But if the wave gets completely absorbed at the other end, the result is a traveling wave. For this purpose, the waveguide is terminated at its end by an impedance equal to its characteristic impedance, so that the traveling wave is maintained from one end to other. To accelerate the charged particles, the speed of the EM wave is electromagnetic wave is synchronized with that of the particle. The particle therefore gains energy from the axial electric field component of the electromagnetic wave, but the magnetic field components remains ineffective, being at right angles to the path of the particles. Okay. The RF radio frequency signal is obtained from a standard master oscillator and is amplified at each feeding station using a clustron amplifier. Okay, okay. The RF signal is obtained from the RF signal. The RF signal is obtained from the RF signal is obtained from a standard master or standard master standard master oscillator and is amplified at each feeding station using clustron amplifier. Clustron amplifier. Okay. Acceleration of electrons. Acceleration of electrons. Acceleration of electrons. Okay. Acceleration of electrons. To accelerate the electrons are disk loaded. Okay. To accelerate the electrons or disk loaded waveguide system is used. The beam of electrons is injected along the axis of the metallic tube of the waveguide, and the phase velocity of the electromagnetic wave is matched with that of the electrons. After the electrons have attained their maximum kinetic energy, they automatically emerge out of the accelerator in the form of the fine collimated beam. Okay. Acceleration of protons. Waveguide accelerators can be used for protons, but the design of such accelerator is very different. The electrons, being light particles, travel most of the time with a velocity very close to the velocity of light. On the other hand, protons gain speed along its total path, as the protons have a much lower injection velocity. Disk-loaded waveguides are not found practicable for phase velocities as low as 0.1 c, but in its place, long cylindrical resonant cavity has to be used. Okay, thank you. And next heading is electric and magnetic field in crossed configuration.